Sketch the graph of any function that satisfies the following conditions. Okay, so let's draw the axis, and then -1, -2, -1, -2, and then you have +1, +2, -1, -2, +1, +2. F of 0 is 2, so that means the graph must pass through this point. F of -4 is 0, so here's -4. It has to pass through this point. And f of 2 has to be 0, so let's say this is 2. Alright, and then f of -1 has to be 0, f prime of 4 is 0. Okay, so 1, 2. You need a zero derivative here. Remember, if you have a zero derivative, that means you have a horizontal tangent line, so the graph could look like this, or it could be sometimes like this, where you have a tangent line that's horizontal that's piercing through. There are two possibilities in that case. So there's a total of 4 possibilities that could happen when you have the derivative equal to 0. Now I think because you already have these 3 points, probably it must look like this, so it has a horizontal tangent right here. So that's like the simplest one, satisfying A and B. So let's leave it at that. But since it could be, it has to be changed for other conditions to be satisfied. Let's just have this in our mental picture and not draw it yet. Okay. And there's also f prime of 4. So at 4, the prime is 0. So it goes like this, and it has to have a horizontal tangent. So I'm thinking of something like this. Okay. Now there are 3 inflection points at x equals to -6, -5, -6. So there's an inflection point. And then at 2 there's an inflection point. Not -2, +2 there's an inflection point, and there's a inflection point at 5. Okay, let's be a little careful here. We decided that this is probably the right curve, and this would be concave down, right? That's concave down, and inflection point means that the concavity changes. So you have this concave down, but then at some point at 6, the concavity changes. Okay. Okay, so there's some kind of concavity here, and the concavity changes right here. And then from concave down, it becomes concave up. We know that it has to be horizontal tangent, so it continues to be concave up. I know that it can't be these. That these also have this point as an inflection point because it goes from concave up to concave down, or concave down to concave up. And therefore, these can't be it. It has to be one of these two. And we choose this one. This is the only thing that makes sense. And then at 5, it has to change concavity like that. Okay. Now there are 2 horizontal asymptotes. One of them, which is the x-axis. Okay, so x-axis has to be a horizontal asymptote. So that means as this thing gets curved, I mean this can't come back up to have this as the horizontal asymptote, because if it goes up, I guess it's possible. No, once it goes up, to have this left side as the asymptote, the curve has to bend like that. But then that would make another inflection point before -6. So that's not going to be possible. So it has to be this one that's getting close to 0. Okay, so we will make it go closer just like that. Okay, and then going here, there has to be another asymptote as you go left. So we will put another horizontal asymptote here. So it has one horizontal asymptote going right, one going left. And E, it has to be differentiable everywhere. That means I can't have any sharp turns or corners. It has to be all continuous. And it looks like this now satisfies everything from A, B, C, D, E, right? Yeah. So there are inflection points here. So let's see, that's an inflection. That's an inflection. This will be a relative minimum. And this one here would be a relative maximum. And these 3 points, well, those are cutting the axis. So these are the x-intercepts, and this is a y-intercept. Consider the function f of x equals to 1/4 of x to the 4th plus x cubed minus 5x squared. Find x and y intercepts. Find end behavior, critical numbers, relative extrema, inflection points, and sketch the graph. This is a long problem, so let's just do one by one. Start from A. Find x and y intercepts. Well, to get the y-intercept, you plug in 0 into x. So 1/4, 0 to the 4th, plus 0 cubed, minus 5 times 0 squared. That's just going to be 0, right? To get the x-intercept, well, you need the value to equal to 0 because the value of the function is y. Set that equal to 0. I see that this gets factored as x squared. So if you factor an x squared out, you get 1/4 x squared plus x minus 5 equal to 0. Okay? Alright, so either x squared equals to 0, which means x is 0, or 1/4 of x squared plus x minus 5 is 0. And because this cannot be factored, you have to use the quadratic formula, which is negative b plus minus, well, in our case b is 1, so negative 1 plus minus b squared, so 1 squared, minus 4 times 1/4 times 5, times negative 5, over 1/4 is all over 2a, right? It's 1/4 times 2a. 1/4 times 2. Okay. And then that's going to be negative 1 plus minus. 4 and 1/4 cancels. Negative negative becomes positive. So you end up with 1 plus 5, which is 6. And then 2 times 1/4 is 1/2. Now you multiply 2 top and bottom to give you negative 2 plus minus 2 radical 6. Okay, so those are the two x-intercepts. So we have the answer, the following answer. Y-intercept is just 0, 0. When you have x equal to 0, you have y equal to 0. X-intercept is again 0, 0. If you plug in 0 is 0. And then also there are two more, negative 2, minus 2 radical 6, 0. These are the values when y is equal to 0, right? So you have this, and finally this negative 2 plus 2 radical 6, 0. Now for the end behavior of the graph, you're looking for limit as x going to infinity. Okay, if you plug in a very large number into x, let's say 1,000. 1,000 squared is 1,000,000. 1,000 cubed is 1,000,000,000. 1,000 to the fourth power is 1,000,000,000,000. So this, although this has a 1/4 in front, this number is far bigger than the other two. So that means it's going to give you infinity, because this becomes infinity. Even if you subtract something, it's not going to do much when x is really large. So that's going to be infinity. On the other hand, you also need to know what happens when x goes to negative infinity. And in this case, again, because it's the fourth power, it's going to make it as positive infinity from here. If you have an odd power of negative infinity, then it's going to be negative infinity, and even power will be positive infinity, but you're subtracting, so it's again subtracting. So you have this going to infinity, whereas the other two are subtracting infinity. However, not all infinities are the same. This goes to infinity much faster than the other. Like I said, when x is 1,000, this is in the millions, that's in the billions, this is in the trillions. So this becomes much, much bigger as x goes to negative infinity. Therefore, this overpowers the other ones and you get infinity. What does that mean? That means the end behavior, see, I don't know what happens in here, but at least towards to the end behavior is it goes to positive infinity as you go right, and also positive infinity as you go left. So end behavior of the graph would be going that way and that way. Okay. Now let's find critical numbers. Critical numbers are where f prime is 0 or it doesn't exist. This is always differentiable, so you shouldn't worry about the case when f prime doesn't exist. So you have 4 comes down, canceling that, so you have x cubed, and then 3 comes down and you have 3x squared, and then 2 comes down, that's negative 10x, and you have to figure out when this is equal to 0. We see that everything is divisible by x, so I'm going to factor an x out, leaving you with x squared plus 3x minus 10. So it's either x equal to 0 or x squared plus 3x minus 10 equal to 0. You can solve this again by using the quadratic formula, but I see that 5 times 2 is 10 and 5 minus 2 is 3, so I'll choose 5 and negative 2 to see if it factors like this, and it checks out, right? 5x plus negative 2x gives you 3x. 5 times negative 2 is negative 10. So this thing factors like this, and that gives you x plus 5 equal to 0, which gives you x equals to negative 5, and x equals to 2 from the second one. So we have the critical numbers negative 5, 0, and 2. Okay, so we got this. Now, once you have these, then you should plug in the, well, you have two choices. You can use the first derivative test or the second derivative test, but since we have to find the inflection points anyways, let's go with the second derivative test. That's easier when you have the second derivative. It's quicker because you just have to evaluate at these points, okay? So f double prime is, let me use a different color. Okay. So f double prime of x is equal to, I'm differentiating this as 3x squared plus 6x minus 10. And okay, and we have And we evaluate these critical numbers at f double prime to use the second derivative test. So f double prime of -5 would be 25 times 3, that's 75. -5 times 6 is -30, minus 10, so that's 35, which is positive. Now, if it's positive, then you have a smiley face, and at the point where you have horizontal tangent, right at the center of the smiley face, you have a relative minimum, right? So we see that this is relative minimum. F double prime of 0 is simply just this last one, so it's -10, which is negative, so that gives you this frowning face, which gives you at the center the relative maximum. Okay, and then f double prime of 2 is 3 times 4, which is 12. And then 2 times 6, that's another 12, minus 10, so that's 24 minus 10, so it's 14, which is bigger than 0. And again, this is a smiley face that gives you a relative minimum. Okay, so you have relative min, relative max, relative min. Now, it doesn't end there, because relative extrema are points on the graph, so you actually have to evaluate the function at these points. So let's do that. So we now know that -5 is a relative min, and 0 is a relative max. So relative min, 0 is relative max, and then 2 is a relative min again. Okay. Now, what is f of -5? -5 to the 4th is 625, and then -5 to the 3rd is -125, and then -5, that's another -125. Okay. Now, 125 can be written as, if you multiply by 4, that's going to be 500 over 4. Right? So that's going to be, well, let's just make this also 500 over 4. Okay. So that's going to be 625 minus 1000 over 4. 1000 minus 625 is 375, so it's going to be -375 over 4. F of 0 is easy, that's just 0. And then f of positive 2 is 1/4. 2 to the 4th is 16. Plus 2 to the 3rd is 8. Minus 2 squared is 4. 4 times 5 is 20. 4 plus 8 is 12. 12 minus 20, that's -8. Okay? So here's the answer for D. It's relative minima happen at -5, -375 over 4, and then positive 2, -8. Relative max happens at 0, 0. Now find inflection points. Inflection points are points where this is equal to 0, and unfortunately that cannot be factored. So find inflection points. You have 3x squared plus 6x minus 10 equal to 0, and since you can't factor this, you have to use the quadratic formula. 6 squared is 36 minus 4 times 3 times negative 10 over twice of 3, so it's 6. And then this is positive 12, 120, 156 over positive 6. Now it's important to simplify this. 156 is divisible by 4. So if you divide 156 by 4, you have 36, 39. So 156 is 4 times 39. That's what we see. And then 4 can come outside as a 2. And since everything is divisible by 2, we're going to divide by 2 and get negative 3 plus minus square root of 39 over 3. Okay. All right. Now, although inflection points are also points where you have to find the y coordinate, this is ridiculous to calculate. So let's not calculate the y coordinates for that, and so we'll skip it. Sorry, I made this number so complicated. Okay. On the exams, the numbers here should be simpler than that. Okay. Something reasonable like when we did the relative extrema. Okay. All right, and then we have to now draw the graph. Let's try to draw the graph now, but we need to have some idea of what this is. Well, you see, here's what we have so far. We have the x-intercepts as first it passes through 0, 0, and it has some two crazy numbers before and after. But what's nice is all the relative extrema. So let's see, if you go 1, 2, 3, 4, 5 steps to the left, negative 5, and then way down here, figure not drawn to scale here, you have this negative 375 over 4. That's very big. It's almost like negative 100, right? 5 over 4. It's a big negative number. And then at positive 1, 2, positive 2, you have negative 8. So compared to this, let's just say negative 8 is somewhere here. Okay, so the graph is somewhat squashed so that everything can be fit. Okay, so we know that it has to pass through this point, this point, this point, and the graph has to be curved like this, because these are the turning points. These are the relative. These two are relative minima, and this is a relative max. So another word for these that you use for polynomials were what we call turning points in pre-calculus. Yeah. So these are turning points. And as we can see, it must have these 2 points as the x-intercept, and we know the x-intercepts. These are negative 2 minus 2 radical 6 and negative 2 plus 2 radical 6. So this point should be negative 2 minus 2 radical 6, and this one should be negative 2 plus 2 radical 6. That's this point. Okay. And then seeing this, you see two points of inflection, right? It's concave up here, and then changes concave down, and then changes the concave up, right? So this point must be the one that's negative. So this point right here would be negative 3 minus radical 39 over 3, and this point here should be negative 3 plus radical 39 over 3. Okay, so that's the graph. And that because we used the derivative information, we were able to locate exactly the points where the graph is turning, and this is a pretty good graph, I think. Okay, next question. Consider the function f of x as this. Find x and y intercepts. Okay, so you plug in 0. Which is 4 times 1, which is 4. That's going to be your y-intercept. On the other hand, to get the x-intercept, you have to set the function equal to 0. So you set this equal to 0, so either x squared plus 3x plus 4 is equal to 0, or e to the negative x over 2 is equal to 0. But exponential functions are always positive, so that can't happen. So the only way to get 0 is here, and that one cannot be factored. Yeah, so it cannot be factored, and you can't even use the quadratic formula, because if you use the quadratic formula, here's what happens. 3 squared is 9, but minus 4 times 1 times 4 over 2 times 1. And 4 times 4 is 16, so you get 9 minus 16. So you get square root of 9 minus 16, that's negative 7. This one is negative 7. And square root of a negative number is an imaginary number. So that cannot be a real number. So basically we find that there aren't any x-intercepts. No x-intercept. Okay, now find the asymptotes. Well, there aren't any vertical asymptotes because it doesn't have a fraction. So by asymptotes, it just means horizontal asymptotes. So for B, we have, before we do B, let's write down the answer for A. Y-intercept is 0, 4. And no x-intercepts. Okay. And now at B, you need to take the limit x going to positive infinity and also limit x going to negative infinity to get the asymptotes. Okay. You have x squared plus 3x plus 4 e to the negative x over 2. If you have a negative power, then that's same as being in a fraction. And we learned that exponential functions increase faster than any polynomial, so they'll just become 0. Okay. All right. On the other hand, limit x going to negative infinity. You have x squared plus 3x plus 4 e to the negative x over 2. If you plug in infinity, here, that's going to be infinity, right? Because infinity squared is infinity. All of these are infinity, so they add up to infinity. Whereas over here, you're plugging negative infinity, right? So this is positive infinity, this is negative infinity, that says 4. But x squared goes to infinity much faster than 3x, so this x squared will win. It will overpower the 3x, so it will be overall an infinity. On the other hand, if you plug in negative infinity here, negative of negative infinity is positive infinity, so you have e to the positive infinity. But you also know that e to the positive infinity is infinity, so you end up with infinity times infinity, which is infinity. So the second one does not yield any horizontal asymptote. This one does yield the horizontal asymptote. So from these two considerations, we see that y equal to 0 is a horizontal asymptote. And this limit as you go to the left, we see that the end behavior as you go left is like that, okay? It goes to infinity as you go left. So that's also another thing that you get out of this, which will be useful when we try to draw the graph. Let's find the critical numbers. To do this, we need the derivative. So to do c f prime of x, well, it's a product of two functions, so we better use the product rule. And this is 2x plus 3 and then for this one, if you differentiate e to the x, it's e to the x, so it's the same thing, but because negative x over 2 is nested inside, you need to make a copy of it and differentiate. So that would give us 2x plus 3 e to the negative x over 2 plus x squared plus 3x plus 4 e to the negative x over 2, and then the derivative of this would be negative 1 over 2. Alright, so we can factor an e to the negative x over 2 out. And after that, I'm going to get 2x plus 3 from the first one, but minus 1/2, so minus x squared plus 3x plus 4 over 2. Now let's make common denominators by multiplying this by 2 and dividing by 2. So that's going to be 4x plus 6, and then minus x squared plus 3x plus 4 all over 2, because now I have a common denominator. And then finally that's going to give me e to the negative x over 2, negative x squared, 4x minus 3x, that'll be just positive x, and then 6 minus 4 will be plus 2 over 2. Okay, I don't like having minus in front of x squared, so I'm going to pull a negative, and also this 1/2, so I'm going to pull a negative 1/2 outside, and the result is you have positive x squared, but the other ones will now be negative. Okay, and that's a lot easier to process. Okay, we're still not done yet. We're trying to find critical numbers. That's when f prime is 0 or f prime does not exist. This is always differentiable, so we just have to find out when f prime of x equal to 0. So we set negative 1/2 e to the negative x over 2 times x squared minus x minus 2 equal to 0. So either negative 1/2 e to the negative x equal to 0, that never happens, or x squared minus x minus 2 is 0. Well, this can be factored as x minus 2, x plus 1. So you get two zeros, you get x equals to 2 and negative 1, and those are the critical numbers. X equals to negative 1 and 2. Okay, now we have to find extrema. That means we need to investigate these critical numbers to see what happens at those points, whether we have a relative max or relative min. And once again, if you have the second derivative, it's easier to use the second derivative test. So let's take the second derivative. That's like taking this negative 1/2 e to negative x over 2, x squared minus x minus 2. I'm taking this and I'm differentiating this, right? So that's going to give me this derivative times the second, and then plus e to the negative x over 2 times x squared, no, not that one, I forgot the negative 1/2. That should be here. Times x squared minus x minus 2 prime. This, we did that just a moment ago doing the f prime. So we know that the chain rule makes the same thing, but then the derivative of the inside function will appear. Derivative of the inside function is negative 1/2. Negative 1/2 times negative 1/2 will be positive 1/4. So that's what we're going to get. On the other hand, this differentiates to 2x and then minus 1. Okay. Now let's factor out the e to the negative x over 2 like before, and you're left with x squared minus x minus 2 over 4 minus 2x minus 1 over 2. Again, we like to use common denominators, multiply 2 top and bottom, and you get e to the negative x over 2, and you get x squared minus x minus 2. Twice of 2x is 4x, twice of negative 1 is negative 2, and the entire thing is subtracted. So it's like this, and then that's going to give us x squared minus 5x, and then negative 2 minus negative 2, so that cancels, so that's it. Okay, so you can write this as 1/4 of e to the negative x over 2 times x squared minus 5x. That's your second derivative. And now let's evaluate these 2 points at the second derivative to figure out what the nature of that critical number is. F double prime of negative 1 is 1/4 e to the positive 1/2 times negative 1 squared is positive 1. Negative 1 times negative 5 is plus 5. And these are all positive numbers, right? So it's positive. I don't care about the exact value. It's positive. Positive means it's a smiley face. If you have a smiley face at the middle, you have a relative minimum. So we know that negative 1 will give us relative minimum. F double prime of 2, 1/4 e to the negative 1, because 2 over 2 is 1. And then 2 squared is 4. 5 times 4 is 20. Well, 4 minus 20, that's negative. These are positive, so this will be negative, which means it's a frowning face, so it's going to be a relative maximum. Okay, so we know that negative 1 is relative min, and positive 2 is relative max. But we shouldn't end there. We actually need the y-coordinate as well, so let's plug in those points. F of negative 1 is negative 1 squared is positive 1. Negative 1 times 3 is negative 3 plus 4 e to the negative 1/2. So that's going to be 2 times e to the negative 1/2. And f of positive 2 is 2 squared is 4. 2 times 3 is 6 plus 4. And e to the 2 over 2 is 1, e to the negative 1. So that's going to be 14 e to the negative 1. So there you have it. Our answer is you have a relative minimum at negative 1 comma 2 times e to the negative 1/2. And relative maximum would be 2 comma 14 e to the negative 1. Okay, now let's find inflection points. Inflection points are you set the second derivative equal to 0. This was our second derivative, so let's copy that down. 1/4 e to the negative x over 2 x squared minus 5x. You set that equal to 0. Well, can this equal to 0? No. So this has to be 0. So x times x minus 5 equal to 0. So x is either 0 or positive 5. Okay, and you really need to check whether the inflection does change. So let's pick some test points. I think we forgot to do this on the previous question. Yeah, the final answer is right, but we skipped this part. Okay, so if we do f double prime of -1, that's going to be well, it's going to be positive here, because exponential functions are always positive. But -1 squared is positive 1, and if you plug in, actually we did calculate this. It was a positive number, right? So it's positive. And we also calculated 2, so let's use 2. We also know that f double prime of 2 is negative, so we know that. And then finally, f double prime of 10 is 10 squared, that's 100 minus 50. So that's going to be 1/4 e to the negative 5, and then times 50, which is positive. So it's going to be positive. So you do see that concavity goes from concave up to concave down to concave up. So that's good. So we know that 0 and 5 are indeed inflection points. And so 0, 5. And we actually have to compute that to find the y coordinates, because inflection points are points on the graph. When you plug in 0, f of 0 gives you 4 times e to the 0th power, which is just 4. So 0, 4 is an inflection point, which also happened to be the y-intercept, right? And then f of 5 gives you what? 5 squared is 25, 15, so it's 44 e to the negative 5 over 2. So that gives you 5, 44 e to the negative 5 over 2. And these are inflection points. So inflection points are 0, 4 and 5, 44 e to the negative 5 over 2. Now let's put everything together to draw the graph. So we had the y-intercept as positive 4. There weren't any x-intercepts. And it looks like, since this is always positive and this is positive, the graph will always be above the x-axis. The asymptotes we found was that as x goes to positive infinity, y equal to 0 was an asymptote, right? We also found that the critical numbers are -1 and positive 2. Okay. And we know that the -1 is a relative minima, and 2 is positive. It's a relative maximum. Okay, yeah. 2 is relative max. -1 is a relative minimum. Everything has to be above the x-axis. And we know that this is an inflection point, so the inflection point should indicate that the graph goes like that and then goes like that. Okay. Now there are inflection points which are at 0 and 5. So there's another one. There's an inflection point here. So it goes like this, and there's an inflection point. It goes from concave down to concave up. And because the x-axis has to be the horizontal asymptote, it has to go down. And we know that the end behavior of the left side is going up, so it goes like that. Okay. So that's it. That's the graph. It's like this, like that. Okay. Now it has to. We should have all the information. So this is 4. This point here is the relative minimum, which is -1, 2 times e to the, let's see, what was it? Right. So it was, oh, this should have been positive 1/2 because we're plugging in negative 1/2. Okay, it should be 2 times e to the positive square root of 2. So this should be positive 1/2. And then at 5, there's, so at 2, we have 2 comma 14 e to the negative 1. Okay. And then at 5 comma 44 e to the negative 5 over 2 was an inflection. Okay. And this was an inflection 2. Okay, so that completes the graph. Consider the function f of x equals the cube root of x, x minus 4. Find x and y intercepts. Again, you plug in 0. F of 0 gives you 0. Cube root of 0 is 0, right? And 0 minus 4, that's 0. Okay. And to get y intercept, you set cube root of x, x minus 4 equal to 0. And that means either x is 0 or x is 4. So the y-intercept is 0, 0. X-intercept are 0, 0 and 4, 0. Okay, so that's done. Find critical numbers. To get the critical number, you have to differentiate. Now, you could use the product rule to do this, but it's actually easier if you first change this into 1/3 power and distribute this 1/3 power to each of them to do the power rule. So you don't have to use the product rule if you just multiply them out. Okay, x to the first power times x to the 1/3 power. Like powers add. If you have the same base, the exponents, the powers add, so it's 4 over 3. And the next one is negative 4x to the 1/3 power, and then you're differentiating this. If you differentiate, 4/3 comes down, subtract 1, so that's 1/3. 1/3 comes down, that's 4/3, and you get x to the negative 2/3. Okay, now we're looking for critical numbers, and critical numbers are points where f prime is 0 or it does not exist. We already see that 0 is a point where f prime does not exist because that's a fraction. To see that more clearly, let's factor the 4/3 out. You see, when you have to find critical numbers, simplifying your answer is a must. So we'll factor the 4/3 out, and then we write negative 2/3 as 1 over x to the 2/3 power, right? So we see right away that when x is 0, this would be undefined, so f prime would not exist. So 0 is a critical number. But to see when this is equal to 0, we have to set that equal to 0. So let's see, 4/3 of x to the 1/3 minus x of 2/3 equal to 0. We can just simply multiply 3/4 both sides to get rid of that. Then we have x to the 1/3. Let's move this to the other side. You get 1 over x to the 2/3. Then what we can do is we can just multiply x to the 2/3 both sides. So they cancel, you get 1. And you have same base, so the powers add up, but what's 2/3 plus 1/3? That's just 3/3, which is 1, right? So there it is, x equal to 1. So we see that 0 and 1 are critical numbers. Okay, now it's asking to find where the interval where the function is increasing. Well, for that we actually have to pick test points and plug it into the derivative. See, before we were using the second derivative test to find relative extrema, but second derivative test can only be used if you can evaluate the second derivative at the critical numbers. That's not possible because for 0, f prime of 0 doesn't exist, so f double prime of 0 also does not exist. So this is a case where second derivative test is impossible. You have to use the first derivative test, and you have this question anyways, so in order to solve C we will need to pick test points. Okay. Alright, so first let's copy down x to 1/3. Let's copy this down. Okay. You have f prime of x equals to 4/3 x to the 1/3 minus x to the negative 2/3, and the critical numbers were 0 and 1. So draw the number line 0, 1. Now pick test points. Before 0 there is negative 1. Between 0 and 1 that's 1/2. And for something in here, since I have to plug it into 1/3 power, I'll just choose something that's a cube of something. So I'm going to choose 8 because cube root of 8 is 2. Okay, x to the 1/3 power is the cube root of 8 is 2. Okay, so let's plug in these numbers. F prime of negative 1 is 4/3. Cube root of negative 1 is negative 1. And remember, this is 1 over positive 2/3, and you're plugging in negative 1. And negative 1 squared is positive 1, and 1 to the 1/3 is 1. So you end up with 4/3 minus 1, which is negative. And that's actually all you need. So it's minus. F prime of positive 1/2. Oh, that tells me actually I would like to have 1/8 rather than 1/2, because cube root of 1/8 is 1/2, and that's easier for me. Okay, so let's do that. F of 1/8, f prime of 1/8 is 4/3. 1/8 to 1/3 power is 1/2 minus 1 over 1/8 to the 2/3 power. Well, 1/3 power is cube root, so this is what you have. You first take the cube root, which is 1/2. That's 4/3 1/2 minus 1 over 1/2, but there's still a square there, right? So that's 1/4. Dividing by 1/4 is multiplying by positive 4. So that's going to be 4/3 1/2 minus positive 4. Oh, so that's negative again. Okay, so it's negative again. And finally, if you do f prime of positive 8, that's going to be 4/3. 8 to the 1/3 is 2 minus 1 over 8 to the 2/3, and 1/3 power of 8 is 2, 2 squared is 4, so that's going to be 4/3 2 minus 1/4, and that's positive, so we know it's positive, which means that since this is the sign of f prime, that means f is decreasing, decreasing, and increasing. Okay, so the only interval where the function is increasing is 1 to infinity. Okay, and as a bonus, we also can answer part D. 1 is the only relative minima. Since 0, you go down and go down again. 0 is not a relative anything, but 1 is a relative minimum. So And if you plug in 1, it's 1 times 1 minus 4, which is negative 3. So you have a relative minimum at 1 comma negative 3 and no relative maximum. Okay, now let's find inflection points. So we need to do f double prime, and since f prime is 4/3 x to the 1/3 minus x to the negative 2/3, we have to differentiate this yet again. 4/3 is a constant multiple, so that can be brought out, and you just have to differentiate each one of these. 1/3 comes down, you have x to the negative 2/3. Negative 2/3 comes down, making it positive 2/3, x to the negative 5/2. Okay. Now once again, x equal to 0 is a critical number for f prime, because at x equal to 0, this doesn't exist. And then if you want to see when this is equal to 0, we know that this has to equal to 0. So we have 1/3 x to the negative 2/3, and we have plus 2/3 x to the negative 5/2 equal to 0. Multiply by 3, and let's rewrite these as fractions. So it's 1 over x to 2/3. This is 1 over x to 5/2. And because we multiply by 3, this is just 1, this is just 2, and that's equal to 0. And seeing this, I guess we want to multiply x to the 5/2 everywhere. So you have x to the 5/2 divided by x to the 2/3, plus 2 times x to the 5/2 divided by x to the 5/2. So that's after multiplying everything by x to the 5/2. Now that's going to cancel. So it's actually 1/1. And if you divide the exponents, subtract 5/2 minus 2/3, that's just x. So you just get x plus 2 as the result, so x is equal to negative 2. So that's your critical number for f prime. And once you have these, then you have to put them on the number line, 0 and negative 2. Oh, actually negative 2 is less. So negative 2 and 0. And let's plug in, here's negative 1, positive 1. And I think I like something that where you can easily take the cube root of, so I'm going to choose negative 8. Okay. And we are going to plug it into here. And you know, I think we need to simplify this. I should have done that before. F double prime of x. See, they both have 1/3 there. So if you pull the 1/3 out, that's 4/9 of x to the negative 2/3 plus, oh, so this should have been 5/3. Interestingly, I did all the calculations correct, even with this mistake. Okay, so you have x to the negative 2/3 plus, not plus, yeah, plus 2 times x to the negative 5/3. And since these are fractions, we can just multiply by x to the 5/3 and divide by x to the 5/3. And when you multiply these two, it's just 1, but this times this gives you x, right? So it's 4/9 of x plus 2 times 1 over x to the 5/3. And 1/3 power is cube root, so I'm going to put 1/3 power and then to the 5th power. Okay, that's our f double prime, and that's a lot easier to calculate. So now let's plug this in, we have f double prime of negative 8 being 4/9, negative 8 plus 2, that's negative 6, and 1 over cube root of negative 8 to the 5th power, that's negative 2 to the 5th power, so that's negative. This is negative, that's negative, so it's going to be positive. That's positive. And then you have f double prime of negative 1. That's going to make 4/9 and then positive 1, and then 1 over cube root of negative 1 to the 5th power. Cube root of negative 1 is negative 1, and then 5th power, that's negative, so it's negative again. Not negative, so it's negative here. It's positive and then negative. And then finally, f double prime of positive 1. Well, everything's positive if you plug in 1, so that's positive. So we have this. So that's our f double prime, which means f would be concave up here, concave down there, concave up there. So we can actually write the answer for f. It's concave up on negative infinity up till negative 2 union, and then you have from 0 until infinity. Okay, and the inflection points, I should have done the inflection points. Inflection points are indeed both 0 and negative 2 are inflection points because there's a change in concavity, right? However, however, at 0, the derivative is, the f double prime does not exist. In that case, you don't call it an inflection point. And it's actually negative 2, that's the only inflection point. So for inflection point, it's negative 2, comma, and you have to plug in negative 2 here. That's negative 6 times negative, so it's positive. So it's 6 times cube root of 2. So that's your inflection point. That's the only inflection point. And 0 is not an inflection point because f double prime does not exist at there. Okay, so now we have to put everything together to draw the graph. Let's first recap what we had so far. So x and y intercept was 0 and then 4. So we know that the graph must pass through 0, 0 and 4, 0. So let's call this 4, 0, 0. The critical numbers are 0 and 1. So at 1, I have a critical number. Okay, and then we also know that the function is decreasing, decreasing, then increasing. So it's decreasing, decreasing, and then increasing. Okay, making this 1 as a relative minimum. And by the way, if you plug in 1, you get negative 3. That's also something that we did. So here's negative 3, so it must pass through this point. So it has to pass through this point, this point, this point, and it has to have this shape. Okay. All right. Then we also know that the negative 2 comma 6 3 cube root of 2, so negative 2 comma 6 cube, it's way up there, 6 times cube root of 2. So this is another point that has to pass, and it has to have concavity like this. So the graph should have a concavity like this, okay, and the graph should have opposite concavity here. That's what we found, right? So it should be concave down. And the reason that this function has derivative undefined at 0 is because it has an infinite derivative. See, if you draw the tangent line, it cuts through this graph, and it's a vertical tangent line. Let me make a different color just to make sure we're seeing this right. So let me erase these. Okay, let's draw in black. So it has to be going down like this. It has to be curved like this, and then curve the opposite way. It should go all the way up. And then from here, now it has to be concave up again. Okay, so it's a little strange. Yeah. And at 0, it has this. It actually touches the y-axis at 0, so that the vertical line at 0 will be the tangent line. Okay. So that's it. That's the final answer. This is inflection at. So we have the coordinates. So I'm just put inflection there. And this one is our relative minimum. Yeah, and we also have the coordinates there, so I guess that's it. It's a rather simple graph considering all the work that we had to put in.